Yeah, hello everyone. I am Afzal. I've been a software engineer over 7 years now. I am quite interested in fault-tolerant architectures, and I like to, tinker around with the latest research in system design, just to find better ways of building applications I've built in the past. Yeah, today the format is we're going to cover a problem space, and then I'll do sort of a DBOS walkthrough. Why do we need DBOS or a workflow? Then we'll do a demo, and then we'll spend the latter part of the talk talking about major features that I found quite interesting. Yeah, so let's get into it. So, as we all know, building reliable services is hard. A lot of the time you get things like double booking when you're trying to pay for something or reserve something. Sometimes you get payment failures. You're trying to reserve for something in a high traffic or highly contested sort of product item. You get reservation error. And then sometimes just the network is down and you have to retry after retry. And then, this is what the user usually sees. But as engineers, this is quite hard to build, right? There's been lots of research in the last 40 years in software engineering to make our services a lot more reliable and a lot more easier to build for developers. So this is an example of what I mean by reliability. So this is sort of a checkout e-commerce example that some of you might have worked in, and most of you have experienced when you're buying something. Usually you buy something, when you're trying to buy something, you've got to reserve inventory, you need to check for credit, process a payment, and then fulfill the order, and then it's success. You got the order, it's at home. But any of these steps could go wrong, right? Reserve inventory, the inventory API is down, what do you do then? Maybe you get to process payment, you've done the other stuff, but payment server is down, or it's not available, or it's giving you a weird error. What do you do then? In my experience, building these kinds of workflow or system, whatever you want to call them, what I tend to see is that the logic to get this working is usually 30 to 40%, but the rest of the code that we write, the 70 to 60% is about managing this kind of reliability. What if something goes wrong? What do you do then? That's what I found in my experience. So yeah, reliability is hard. Steps can break for any reason. Resource exhaustion, timeouts, unreliable external APIs that don't provide idempotency, and then you have to build your own idempotent infrastructure if you don't want to double call it. And outages, right? Even for big cloud like AWS, Google, sometimes they have not that reliable APIs. And now we're in the world of AI, obviously, and AI makes everything harder, right? We've got those problems, and it brings a new set of challenges in reliability. So that's a workflow. It's sort of a deep research agent workflow. And let's say you search for a topic, you type in Postgres or Golang, for example, and it does a bunch of steps, and at the end it produces a report that you can then you can verify if this is a report that you want or not, you want to rerun it again or not. But again, this can be mapped into a standard workflow, and each of these steps can fail for a variety of reasons. The thing that we talk a lot about work and we're worried about is token spent. So this is an agent with 5 steps. What if you have an agent with 20 steps and that is being used by many, many customers? What if that fails? What if one of the API on the 15th step just has an outage and a lot of the workflows just fail? And what do you do then? Like every time your agent calls an API, an LLM, a model provider, you're spending tokens. And if you have to restart those, you're spending the tokens again, right? And you need to architect your application in a way that you're not trying to make OpenAI rich, right? By just spending all your token budget if something goes down. And then again, unpredictable code paths. And what we mean by that if you run the same agent again, is the output that it gets again, they're non-deterministic. You don't get the same output each time. So you have to think through that and think about that. And rate limiting APIs, we all know that we don't get unlimited calls with LLM providers. You need to be able to rate limit your call. Anthropic is one of them that suffers from many outages. So you need to handle that when that occurs. And then I think another big one that we'll cover is sort of logical backout. A lot of agents these days, they're just reads, right? They're just reading, and then summarizing something. But what happens when they start writing things? What happens when whatever they're writing is quite important? Can we provide them an infrastructure where an agent prone to mistakes can easily back out of that and compensate for that mistake that it made? So again, building agent applications, they do need reliability. And in my opinion and experience, workflow engines that I've been building in the past for the last 30, 40 years as an industry can really help with these types of applications. So when we talk about workflow engines, what do we really mean? What does a workflow engine really do in its essence, right? And to describe that, I would talk about like a game example. Many of you have seen this. And if you're playing a game and you kill like a few bosses and then you get to a stage and maybe you need to go you need to go to the toilet, or maybe you want to play the day after, you want to be able to save the state, okay, of the game and then restart it whenever you want, okay? And that's something we call in software engineering checkpointing. You want to checkpoint the state at a certain stage of the application. This is called the game gets checkpointed when you save it. And if you design your application around checkpointing, what is it that you want to checkpoint? You want to checkpoint the behavior of the application. So every time it does something, every time it executes a function, you want to checkpoint that. And there's a terminology around it now. The industry seems to be calling it durable functions. Durable functions, in their essence, are these functions whose output has been checkpointed to a database. So if you have multiple chain functions, you can and a few steps crash, you can start again from where you failed, not from the beginning again. And then durable function, obviously nowadays offer a lot more than just that. So you probably know about these things, and these challenges are nothing new. They have been addressed by systems that we've been building as an industry. So a few big names are temporal, airflow, cadence, step functions. I've used a lot of step function in the past. But a lot of these systems really, what they tend to do is when you bring them into your application, into your world, you have to re-architecture your application, your code base to the specificity of these systems, right? You have to change your the project structure. You have to do a lot of heavy lifting to be able to submit tasks and start working with these orchestration systems. And for example, with step function, you have to declare a really weird DSL in JSON to get data moving from one point to another point. So it's to me, this doesn't feel like the best UX you can offer to a developer. That it takes a while to get your application configured to become a durable application, to become a workflow that can recover. So can we do better? Okay, before we address that, so this is a common design pattern that a lot of these systems share, right? You have your API server there, and then you have an orchestration server, and then you have the various workers that are working, and then you have the data store that the orchestration server saves the data to. And basically you have a manager and then a bunch of workers, and the workers have to keep talking to the manager. When can they work? When can they submit work? What is the next step? So here you're not just managing your workers in case of failure, you have to also manage the orchestration server. So the complexity of maintaining or self-hosting this kind of system is quite high, because there are two types of distributed systems that you have to support in case of failure. And then the data store as well is decoupled from the orchestrator server, and that has its own challenges in terms of observability, analytics, right? You want to understand how your system operates, then building that in-house can become quite a challenge. Yeah, so to me the UX doesn't feel great. Can we make things simpler? And simpler for me means, can we get better performance, low reasoning complexity for the developer to reason about an orchestration system and start working with it and bring it to its application and use the potential of it. And can it cost less, right? So as in my experience, when something is complex, it also means it costs more. And when something is simpler, it means that it costs less too. So I've been following, because I like to tinker around, I've been following this project for a while now. It's been about 2 years. They've launched as a startup. It's called DBOS, Database as Operating System. It's a really cool concept. And it was started by Mike Stonebreaker, who's the creator of Postgres and many other innovative database technologies. And myself, I consider it as a system design innovation from first principle to build applications. And basically what it is that it's a workflow engine that is a library, an embeddable library into your application, right? What do we really mean? And the key thing is this, all right, this bit here. This is just your Postgres database. Your central orchestrator is a Postgres database. It's not an external server that you need to maintain. It's the Postgres database becomes your orchestrator. And in there you can have workflow orchestration, queues, messaging, and many other advanced features. And what your applications really have to do, and we will see those, is just install a library, go get, right, and start using it. You don't have to do more. Maybe a few things in Terraform, and then you're up and running and you got a durable application. And you don't have to re-architect so much your application that it becomes difficult to reason about for it. So let's go through it. So we've got standard workflow, in this case a deep research agent. You've got these steps, and if I was running this workflow using DBOS, what would happen is when someone starts the workflow, we checkpoint the database. So if I type in find me the best database, we checkpoint in the database that there's a workflow that has been started with a pending status, that it's working now with an ID. And then you move to the next step, and then goes plan, does something, calls an LLM. Okay, there's this query about databases, create a plan on how I want to search it, goes to the LLM. Once we get the response, we checkpoint in the database back in again. So in here, step 1 has been checkpointed, and the output is the search plan. It'll be like the big string that you get back from, it'll be your big plan that you checkpoint in there. And the next one is search. So you start searching, which is the plan will determine what you want to search, and you run a bunch of query in a fan-out fashion, and that step just searches, and once you get the response, you checkpoint again to the database. And for whatever reason, between search and synthesize, whatever reason, it just fails, right? There's a network outage, there was a hardware crash, and then maybe a few minutes later, your application comes back online. Because everything is checkpointed into the database, your worker goes there and says, okay, there's a workflow that's impending. Okay, it has already executed plan and search step. I've already got the output of that. I only need to run synthesize. So skip all those steps that have been already run, and it'll go directly to synthesize. And it runs synthesize, which is sort of summarizing the whole search that was done. And then it'll go to human in the loop verification, and then you can approve or reject that, and the workflow just completes. So that's really what we mean by checkpointing, what we mean by durable functions, workflows, and that's what, in a very simple way, what you can do with Postgres. But we'll look at more advanced features. So a demo. And now I'm starting to pray everything works. So if I go back to my terminal, that's running. So here we got a research agent. It's a deep research agent that basically makes a call to an LLM, gets a plan, and does a fan out of searches. Once they're done, then goes back to the LLM, summarizes it, and then it presents it to the human to verify the output. Okay, so I mean, let's run something. What's a good query? Maybe who's Andy Burnham, right? And then we launch the agent. So right now, this is in the planning stage, and I could just crash the app. I just crashed the app. Maybe that wasn't the best time to crash it, but if we run the application again, we'll see this coming back online, and it's running from there too, again, and started the searching. So we crashed our planning. It had already checkpointed that I've started a workflow, and that was and it has the input of the workflow. And now it's running the searches. This is we're doing a fan out, and what I can do now is crash that as well. Okay, we go back. So we've seen that one search was done, right? So we launch it again. And it has continued to search, and he skipped this one because he has checkpointed that I've done it. And obviously this is going to take a long time because it's connected to my phone. But once this ends, you could crash at any point, even if you had 3 searches done, and it restart from where it until has checkpointed to. But at the end, what it does is you get to when it finishes the search. This is a query we run earlier. You get to a human in the loop scenario. So this is a human in the loop. So here you can approve what it has done, or you can just select finish, or you can get it to search more queries. I'll press finish, and that marks that workflow as completed. Okay, that's still running. It's okay. We'll go back to our slides. Slideshow. So again, I think I want to hammer this point in about checkpointing, because I find that people they don't understand it or they forget about it. Is that when you start the workflow, you checkpoint the input. That's what we saw when I just stopped at the first step and it booted back up again. And per step, you keep checkpointing the output, not the input of the step, but just the output. And then at the end, you checkpoint the workflow output that it has completed, and you checkpoint it to a database. Now let's look at I was saying earlier, this is an SDK you download and you introduce it to your application and you can easily write it. So let's look at how that looks like in terms of coding. So here you got a very simple search function. It's a plain Go function that just calls Gemini to do search. You have to make sure that you meet the interface. There's a bit of, you have to change a few things, but it's not too many things. You have to just match the interface of the library. So that's a standard function. And the way you convert that function into a step is that you wrap it by calling the library, and libraries run as a step function. And you just embed that in there, and it becomes a step. It'll work on its own and just automatically checkpoint the output of run as a search. So in the case after you rerun this bit of the code and the server crashes there, your code, the library has already checkpointed the output of that function. Upon restart, it won't execute that bit anymore. It'll continue, it'll skip that. So, and then how do we convert steps into a function? So you basically create a search workflow function. You match the, you just have to make sure you include the DBOS context, and then you declare your step inside there, and make sure you wrap it into run as a step. And that basically turns it into a workflow. And that is sort of the big workflow that I've got in there. That's how it looks like, the deep research agent. Here is doing the search bits, and it's sort of fanning out. And in order to, you have to register your workflows as well. After you created your search workflow, you've got to register it before it starts. And then with handle. So you run your workflow using the library, dbos.run workflow, and then you just wait for the response. So this is like an embeddable library that you can quickly start using it and convert your code into a workflow. Again, it's sort of, the main thing here is Postgres, and we look at how we can use things like queues messaging within Postgres, not using external messaging services or queuing services. Of course, I had to get that. Sorry, cursor haters. So let's look at some more advanced features. So human in the loop, right? Human in the loop is very important for agents. I think for most of your agents that at least are doing some kind of write or producing some kind of report at the end, you need human in the loop in there. And there are various ways, different people building human in the loop infrastructure in different ways. Usually it's mostly event driven, some kind, right? It's async because you have to wait for the human to just approve it, analyze and approve it. So how can we build human in the loop within DBOS, within Postgres itself, without the need of an external broker, queue, or whatever you want to call it? And I think this is the magic of OLTP databases like Postgres that have been maintained by open source communities, that they have progressed a lot in the last 30 years. Like, they have been building features after features in the database that is quite scary when you read the manual of how many features it has. So the way this works is, I have many bullet points, but I got an LLM to convert this into a picture. So hopefully this, it hasn't made a mistake, but hopefully this sort of makes a bit more sense. Basically, once we want to do human in the loop, we want to wait for someone to reply. The most important thing you do is that you've got a notification table and you write a row in it. Okay, I'm waiting. And make sure that the row has, as a consumed false, that row has not been consumed yet. Okay, and that then has a trigger on it, which then starts listening for it in the channel. And then when someone sort of approves that the human in the loop presses yes to finish, then you reply back to that channel, and then you convert this row into true, that has been consumed, and then that human in the loop step is done. Okay, and all of this is handled by your library, the DBOS library, by just writing SQL into Postgres. Right, when you go into, I've went into the library a few times, it's just SQL, right? Writing into a table, you've got trigger queries written in there, and then using the listen notify feature of Postgres. And two functions are being used: DBOS send, which starts listening for an event, and receive and then send. Receive starts listening, it stops the workflow there until someone sends that event, and then you can continue. And then let's look at how that works on an application level. So you've got your browser, your server, and then the database. And at the browser level, I've got agents that's polling the server and is requesting if an event was registered on a workflow events table. Okay. Basically, when you create the human in the loop stuff, is that you write a row into the notification table, and then which is something that you can modify. It's a read-write table, but then you write a read-only row into the read-only table workflow events, and the browser is polling that table, checking if there's any events on that table. And that's basically how you can just configure human in the loop, an event-driven architecture within a database, without having to go and seeking for other infrastructure that your application might not need. So if you got a poll of every 30 seconds, keep checking if there's anything on that table, and then if you approve, then the server approves that, and there's a query that's run on the notification table that changes the consumed from false to true, but that's done. And that's how the application keeps working. It listens to that table. And that's how you can achieve human in the loop through Postgres, and you don't need a broker for it. Which I, as a someone that's interested in system design, decreasing the complexity for a developer, especially, I've debugged many, I've been on many incidents, and they've been sort of Frankenstein application architectures, and they've been really hard to debug them. And a simple architecture makes it always easier to do that. So if you guys, this is another pattern, but another problem, sort of the fan out problem. So when we were doing the search, we had a planner that generated a plan to search, and then we run many searches in parallel. So that's the fan out that's happening. And the classic fan out just breaks with LLM. So any of these search calls could fail, right? So what do we do then if we don't get the response? Because we want to synthesize on all of those calls. And again, the calls are expensive. And then you're always rate limited on these queries. Like if you're running too many fan outs at the same time, you get the 429s, you can't run anymore. So how do we solve that? You make your fan out durable, first of all, in case of failure, like we saw earlier, right? We failed one search and we could easily bring it back. So each search gets checkpointed. Each search basically becomes a workflow. That's how I configured it. Every search is a workflow. So if it fails, but then some of the other paths, then that's been checkpointed to the database. So when the application restarts again, you only run the one that have failed. And another really cool thing you can do with Postgres is that we'll look in a bit that you can use tables to configure queues. And via that, you can solve the rate limiting problem. You can define it within code that I want you to only concurrently do 3 searches at the same time, right? Concurrently run 3 searches, not more than that. And then you can do that via queues table inside database, inside the Postgres database. And you can solve some of the rate limiting problems or rate limited configurations, right? Because you have to configure based on what you can use. And yeah, queues are just a table, a durable ACID table that you write a row to, right? So you basically enqueue a task, you keep writing tasks to a table, and with the status of enqueued, and a worker goes in there and picks up the first task and changes the status to pending, so it's working on it, okay? And yeah, that's how you declare the queues via code, right? It's a simple code. Here you can, there we go, you create a new workflow queue, you can give it a queue name, and then you configure the concurrency model. So at the same time, only 3 workers can work on a task. So one worker can only pick up 3 tasks, not more than those, because of some rate limiting limits that we have. So I think this is where it gets quite interesting, where I found that databases has a lot to offer. Where, let's say you've got a bunch of workers and they are competing for the same workflow, for the same task, and there's a lot of contention, okay? So usually to solve this kind of contention, you have to write your own locking mechanism, you have to build your infrastructure around it to make sure the locking works correctly. There's a lot more involved there to make sure that a worker is not picking a task that another worker has picked. But with the database, this kind of problem has been solved within the OLTP type of databases of locking and unlocking. They've been working on this for the last 50 years. So in order to just solve that, when you pick up a work, at the end of the query you write, just skip locked, skip the rows that have been locked, and it just skips them. And it's just one line of change. You've not written any mutexes or any logic to do that, because the database has that built in. So in this case, you have your workers that are just only working on 3 rows, and they're skipping rows that have been locked by a particular worker and only picking the other ones. I know we are short on time, but I'll quickly jump through all of these. And because the queue is a table, and this is another powerful feature, everything in the database is observable by the most used programming language in the world called SQL. You can write SQL and you can observe the state of your system because everything is just a table, right? If you have, for some reason, let's say you have a consumer that has failed and is not picking up work, and you want to identify how many tenants have been affected by a consumer that didn't pick up a work from a table, you just write an SQL query. You don't have to learn a CloudWatch query language that takes you 3 days. You just write SQL, something that most of us just learn. And then you can do partition queues and idempotency and the things that you might want from other systems. So yeah, I think that was my talk. So the conclusion here is, actually, before we go to the conclusion, this is another feature I quickly skim through is agents can make mistakes. So most of the agents that you guys use are just reads, or maybe you have built a reads. But what happens when they become write agent? What if, and agents are prone to making mistakes as well. How do we provide them infrastructure, a way for them to just recover from the mistake they made without us having to continuously be in the loop and us having to do work because they have made a mistake? One way is via compensation. And guess what? Compensations is a technique that's been well designed, well documented, and developed by the database community for a long time. And it works very well in high traffic agent systems. So databases are great also for agents that make mistakes and they want to compensate on that mistake. And these techniques have been well researched and well documented, and you can just easily write that with an embeddable library that talks to your database. A quick one, this one, I think a question that I get a lot, can the database be a performance bottleneck? So per workflow, you have to do 2 writes every time you create a workflow. One write is the input of the workflow, and then the one write is, and one write will be the output of the workflow right at the end. And then per step, you have one write to do, which is the steps output. And each database write is around 5 milliseconds, right? So your performance really is your n number of steps plus 2 writes that you do with a workflow, and that becomes your latency, your performance of the system. And a large size Postgres instance can handle 5 to 10,000 steps per second easily. And I was talking to the DBOS team, and they did a benchmark where a good Postgres, well-configured Postgres, can handle almost 12 billion writes per day, or 4 billion workflows per day, which is more than enough for most applications, right? And if you needed more for whatever reason, right, your agent was doing a lot more work, you just scale, you shard your database and scale horizontally. Another technique that's been covered very well in the database community. But what this type of application are good for is high latency, high trading frequency kind of application, where 5 milliseconds is too much. This kind of approach is not good for that. And always remember, if you're using this approach, your database will always be your biggest bottleneck in terms of performance. And as you increase the number of steps, because this is a much simpler system, they did a benchmark against step function. Step function has an orchestrator in there and is speaking to different storage system, right? So the more steps you have, the more latency you have, okay? And the more steps you have, it just goes up by a factor of 25 compared to just DBOS, where the data is very close to you, and if you have the same application data in the same database, your application is really fast compared to some of these other systems. But advanced application need more than that. You need more mature observability, schedule jobs. You need workflow versioning, patching, identities, and then things like communication. So yeah, that I think we're doing well on time. So in conclusion, don't forget about reliability when it comes to agent applications. AI agent applications are bringing new challenging reliability problems that we've probably not experienced day to day before. A workflow engine can help to deal with some of these problems. And then my favorite is DBOS, which is a library-based workflow engine that I found to be easier to operate, easier to understand, and just a good engine to operate. And I think that's it.